Alright, this lecture is going to be on the electromagnetic spectrum. And the electromagnetic spectrum is often written as the E&M spectrum. And it involves radio waves, which are your low frequency, large wavelength waves. And as we increase in frequency, therefore decrease in wavelength, we go into microwaves. We go infrared, visible light. Notice that the red end is on the radio end side, and the blue-violet end is on the higher frequency end. So I move from visible light into UV or ultraviolet, into X-rays, and into gamma. Notice gamma are the highest frequencies, so therefore we call them, or we say they have the highest amount or greatest amount of energy. So waves in the electromagnetic spectrum vary from large wavelength, low frequency radio waves to very short, small wavelength, high frequency gamma rays. Energy is measured by frequency. So the higher the energy, higher the frequency, the higher the energy. So mathematically, wavelength and frequency are inversely related. When you multiply them by one another, they equal the speed of light. And technically, we could say the speed of light in a vacuum, or in the vacuum of space. Therefore, all energies on the entire electromagnetic spectrum travel at c, and that's the speed of light in the vacuum of space, or 186,282 miles per second, or 300 million meters per second, or 300,000 kilometers per second. That those are all equal values. And they travel, or they move, in the form of photons. That visible light is only a portion of the electromagnetic spectrum. Our eyes are designed to interpret energies at these wavelengths, and that's where this little tiny segment comes in. So the electromagnetic spectrum, here's a video you can watch. I recommend you go back and watch this. Take a look at this screen, the PowerPoint lecture on your own. But once again, we're just reiterating the size of the wavelengths are getting closer together. So a smaller wavelength as I move from left to right, and therefore my frequency is increasing, and therefore the energy is increasing as I move towards the gamma side. And here we're corresponding color with this as well. We're saying that the blue and the violet have the highest frequency and therefore the shortest wavelength compared to the red, orange, yellow, green, right? This end of the spectrum are larger wavelengths, lower frequency. So red has the largest wavelength, it has the lowest frequency. And notice as I go from red to orange to yellow to green, the blue to violet, I'm changing both wavelength size proportional to the frequency change. And here if I take white and I separate it in a prism, if I separate it into its individual components, I would get the red, orange, yellow, green, blue, violet, the Roy G. Biv colors. And once again, just to reiterate, each one of these properties, you cannot further subdivide these. These properties, red is red, and you cannot further subdivide these. So I have you do a couple of different activities just to make sure you can kind of just reiterate what these are, right? These colors are parts of white light, and therefore when we look at the additive and subtractive color process, it'll help make more sense by learning electromagnetic spectrum first. And here's the last little part for you. I found this picture from a friend of mine who does photography, urban photography, professional. So a local photographer took this picture. I call it the moose is loose. Describe what is going on in the picture that was taken and how and why the colors look the way they do. So notice it's a really cool urban picture that I think you can have some fun with. So have a parent, a guardian, have somebody around, maybe even a student from class, and check out what's going on with the bubble gum